there.
I still feel bad, but
Like it threw away all his own tests that he made, and then now he can book it. That's why we can book tests now.
I would have said no. If I would have thrown my stuff away, I would have come back. Can you imagine after 4 years of teaching being a first year teacher again? No way.
Yeah, well, he just doesn't.
No,
he
it's
just
just
read the
he
book,
uses
they'll
the
give
ones
you the
in the
book
book.
test.
Really?
Book tests are
Which-
harder now.
What is
You know, I
Or-
don't. I'm a little less strict about that in his situation because of what happened.
Right.
Oh, look at that. That's weird.
Is it out of focus or something?
Well, I haven't been able to figure out how to get an equation that I put into Word to come up
Oh.
in PowerPoint when I copy and paste it.
Was it the JPEG then?
I
Or
don't
PDF?
know.
Picture file.
Yeah, I don't know.
Yeah.
Okay, so far we have kind of considered your electrochemical cells, your galvanic cells, okay? In a very practical fashion, we haven't really talked too much in theory, so we're going to spend some time talking a little bit in theory. We're going to relate electrical potential to Gibbs free energy. If you thought that was possible, it's actually pretty simple, okay? Now, when we did a cell, a galvanic cell, it creates a potential. Okay, that forces electrons through a wire from one side to the other. Okay, from the anode to the cathode. Those electrons can be used to do what? To work.
EMF. Magnetic force. What is the M?
It is. I cannot remember off the top of my head.
What does M stand
I can't remember. It's like it's something force. It might. I don't know if it's electromagnetic.
Electron magnet.
I'm not sure it even says in this textbook because I read it this morning and I don't remember it. It did say in my physics textbook, but I can't remember
I'm just
off
gonna
the top of my head. You just say EMF of a battery, that would probably.
Electromotive force.
Electromotive force, yeah. Okay. So basically what an EMF stands for is, think of it as the potential energy stored up to pump electrons from one side to another. You've got to have a potential energy difference for energy to flow from one side to the other. Okay? Now, we've been talking a lot about potential difference. There's very little difference between an EMF and potential difference. Well, I'm going to use them interchangeably. Okay, kind of like I did enthalpy and heat. There's a very subtle difference, but they're very, very similar that I'm just going to kind of treat them this way. Now, if I have 1 volt, I'd be able to do 1 joule of work via 1 coulomb of charge. Okay? That is an equation that we are going to show up. You guys have this in your notes? E equals negative W over Q, I believe.
Yeah, we have
Okay. So the work that can be accomplished when electrons are transferred through a wire depends on the push of the electrons, or the force, the EMF / potential difference that you have across your cell. So if you have a big potential difference, it essentially pushes harder. Current flows faster, more work is done. Okay? The driving force, or our EMF, is defined as in the terms of potential difference, or volts. Another derived unit for volt, what it is a joule per coulomb. Have I talked about a coulomb with you guys at all?
No.
Okay, a coulomb is the unit of charge.
And then things like Coulomb's law. I don't know what it is.
Yes, so we use Coulomb's law in that it was the charge of our proton and our electron. I don't know if you remember that. It was a while ago. But a coulomb is the unit for charge. Okay? just quickly, I don't think this is an overly difficult sign convention. We have talked a lot this year of sign conventions, but from the standpoint of electricity that we're going to be dealing with and its ability to do work, okay, if work is flowing out of the system, then we're going to have a negative work, and if work is flowing into the system, we're going to have a positive work. Now, with most of these galvanic cells, we would expect negative work, because we would want to do work on the surroundings, right? Allow electricity to run through a wire to do work on a light bulb, or on a motor of some sort, or whatever it is that we're trying to get power to, all right? So you're going to see that a negative work gives us a positive cell potential. Okay? Do you remember when we were doing cell potentials with the two half reactions, and we always worked it out so that you always got a positive cell potential? Do you guys remember that? Okay? And that's what you're going to see here, because a positive cell potential will give you negative work, which means doing work on the surroundings.
Yeah.
Which is what you would want. Now, can you have a negative E? In fact, it is very possible to have a negative E. We will talk about it this section, how you can have a negative E. The reason why we made everything positive is because the goal is for us to do work. And so we just made everything positive when we were doing it the past couple days. Okay? That's not always the case. And we're going to talk about how for a positive E, that is a spontaneous process. A negative E is not a spontaneous process. And so we're going to talk about, okay, can we predict if a reaction is spontaneous based on the cell potential it has? Okay, and that's what we'll do today. So, okay, so from the equation I just showed you, the E equals negative W over Q. Okay? We can see that the maximum amount of work done is when we have a maximum cell potential. Okay? However, there is a problem, as you might imagine. When electricity starts flowing from one terminal to the other, there is a certain amount of resistance in that wire. What I mean by that is some of the current will rub against the particles inside of the wire, causing friction. Okay? That's why wires usually are insulated, right? Is because there is a certain aspect of resistance even in a metal wire. Even though it's a good conductor, there's still some resistance, so energy is lost in the form of heat or friction. Okay? So if that's the case, okay, when current flows, energy is lost to friction, so the maximum work that we could have obtained was never obtained. Because some of the energy that we wanted to use to do work got dissipated in a form of, to a different form of energy that we did not want. This is basically the second law of thermodynamics at work. What is the second law of thermodynamics state?
The entropy one?
Yeah. There's basically two ways of wording it. You could say, right, that things are spontaneous when the entropy of the universe increases, or another way of saying that is things go from order to disorder, and another way of saying that is we always lose energy along the way. Some of the energy that we want gets dissipated into some other source that cannot be used. Okay, you've probably heard that there is no such thing as a 100% efficient machine, right? That's because we cannot use, not all the energy is usable. That doesn't mean we're destroying energy, it's just not all usable. Okay, this is an example of that. If we didn't have any friction in the wire, then all of the electrons' energy would be used to do work. Okay? But since there's friction, some of the energy that we wanted to use to do work gets lost in the form of heat or friction. Okay?
From machinery.
Yeah, there's other energy forms, not in the context of this.
Oh, right, yeah.
Okay? So this really reflects the second law of thermodynamics. Some of it's wasted, and so the work, maximum work that we would expect from the cell potential being max, we will never get the maximum work because of energy lost. So let's tackle this problem. So it says suppose a certain cell has a maximum potential. So that is assuming that no friction, no energy is lost. That's what our cell potential would give us. Okay? In a particular experiment, 1.33 moles of electrons are passed through this cell at an average actual potential of 2.1. So what they're saying is, due to the resistance of the wire and other things, this is what we actually get for a potential difference. In theory, we should have gotten 2.5, but in actuality, we only got 2.1. Right? What is the actual work and the theoretical work if 1 mole of electrons have a charge of 96,485 coulombs? This is a constant that you're going to need to know. 1 mole of electrons is that much charge. It's called a farad. Discovered by a guy by the name of Michael Faraday. You may have heard that guy's name.
Wow, Faraday keepers are so cool.
Yeah. He did a lot of work with electricity and electrons. Right? So, just make sure that you know that 1 mole E equals 96,485 coulombs. Okay? So, we know that I'm just going to manipulate the equation I gave you earlier to solve for work. Negative Q E and another one that you may or may not need, because we'll kind of do it kind of separate. The Q, or the charge, is the moles times, whoopsies, N times F. And do you remember what I said F was? That F is this. It's the farads. Okay? So in this particular problem, it told us we had how many moles of electrons? In this question. 1.33 moles of electrons. Well, I want to know the charge of those electrons.
Multiply it by the.
So we're going to multiply it by the farad. So for every 1 mole, I have this much charge. Right? So that will give me Q, because moles are going to cancel out, and coulombs is our unit for charge, which is variable Q. Okay? Second time, I'll just give you what this is, 128,000. 3Q5 said?
Yeah.
Yeah, let's go 0.1, is that cool? Alright? Now we're going to do then work actual and work theory. Okay, we know the charge is going to be the same in both situations. We're just going to have a different potential difference, or cell potential. So our actual then, and our cell for our actual was what? 2.1, and I'm going to put it in units that make sense. I said a volt was the same as a joule per coulomb. So that will allow our coulombs to cancel out, giving us our work done in joules. I need my negative here. My bad. Same idea for theory. Same amount of charge, just different potential. Now, in theory, we're going to do more work, and this should make sense. Remember I said potential difference is like the charge pump, or the force that forces charge through. So if you have a stronger force pushing electrons through your current or your circuit, you're going to get more work out. Does that make sense, everyone? Okay? So, in theory, we're going to do more work than actual.
Is that supposed to be -5?
Nope. Sorry, good catch. Okay? So this is my actual work done. This is in theory, had there been no friction. Lastly, they want to know how efficient was the cell.
84%.
84%. So you would just take your work divided by your work max, or you could say your actual over your theoretical times 100. So you would take this divided by this times 100. When you do that, you will get your 84% efficient. I didn't put in the numbers, but you can, I think you can figure that out, right? It would just be this.
Theory is worth
Okay, the maximum is always going to be in theory. Okay, and this is always going to be your actual. Got it? Okay, well, there is a relationship between the potential of a cell and your change in G. Okay? Your change in G is equivalent to the maximum amount of work you're going to get. So if that's the case, with a few manipulations, we're going to get this. Due to time, I don't really have enough time to show the derivation, but what it basically is using that first equation I gave you and taking NF and plugging it in for Q. Because I said Q equals the moles times the farad. Okay? This equation states the maximum cell potential is directly related to the free energy difference between the reactants and the products. This should make sense. You're going to do work equivalent to your difference in free energy. Okay? If a reaction is going to go from high energy to low energy naturally, you could use that energy to do work. Right? So when we have a cell potential, okay, the reason why we have a cell potential is because a reaction will spontaneously go from high energy to lower energy, and we can use that energy then to do work. So, we've got an equation. Using the table of all the half reactions and the cell potential, can we figure out the change in G of this reaction and find out if it's spontaneous? Do you guys remember what the sign needs to be for change in G for it to be spontaneous? Negative, okay, good. So what we need to do is we need to find the cell potential so that we can then find our change in G. Okay. So here to here, that's going to be reduction or oxidation? Here to here, will be oxidation. And you see how 2 electrons are taken, 2 electrons are given. And so I don't have to worry about balancing any electrons. It's a pretty simple situation. So let's find the cell potential for each of these half reactions. You have to look in your book for the sake of time. Can I just give them to you? In that table, your cell or your half reaction potential for copper, okay, is 0.34. And your cell potential for your other one is negative 0.44. So our E cell .34 minus a negative 0.44, giving me a 0.78 volts. Yeah. Just review kind of like from the other day.
So you can even solve the whole thing as long as you know the sign of the E.
Yeah, technically, if I know this is a positive E, I could tell you it's spontaneous right now. However, you're probably going to need to, I probably will want you to compute the actual.
Right, you can't without moles here.
Yes, that's why we need to do the half reaction. That's what I forgot. So let's say, well, how many electrons did we say we passed? Okay, so we went and, let me just show you this quick. Plus 2 electrons. So for every 1 mole of these, I give off how many moles of electrons? 2. So that's what we would put in then for N. If this was, say this was 2 and this was 3, and I have to multiply, do the least common multiple for that, you would use 6 moles and you would plug that in. Does that make sense? Okay? So you're always going to use the number of moles of your electrons that are transferred when you plug that in for N. Okay? And you should figure that out after you've balanced everything like we've been doing for all the oxidation reduction reactions up to this point. So you would get negative 2 moles. And what do we say F was? I don't remember that number off the top of my head. 96485. And our cell potential is 0.78. When you do that, we'll see that we will get a negative change in G, so it is we are done. I know we can get to the last problem. I'll start with that tomorrow, but you can read on it. What I would do is, there's just one example in your book on predicting spontaneity that it would be wise for you to read. It wants to know if you put gold in this particular acid, will the gold be reacted and dissolved or not?
How does one?
He's only getting 2 days a week.
How does that work?
Well,
How does it?
so like a mechanical energy would be any form of potential energy. So if you would like think of like a hydro, right? Water, potential energy.
Okay. Yes.
So,
I understand. I understand that one. But the other way around there. Oh, okay.
Yeah, it's right there. Thanks for inviting me. I try to hide my conscious identity.
I've been to your house.
Do you remember that? Did I ever tell you that like when he was like, hey, I'm gonna look your house up and Oakland County Assessor and keep your house? Do you remember when he came in and said an address? Do you remember that?
No.
That wasn't my address. Did I say that to you guys?
Yeah.
I was like, that would have been really awkward that he went and he viewed that house and then it'd be somebody else's house.
Work at Saturday.
I got my paintball gun now, so if anyone wants to try to teach me my house now.
Oh! Hey, what are we doing tomorrow?
Oh,
Paintball's so much fun.
That's a good,
Especially when you're shooting in
that's
the
a good incentive for.
What are we doing tomorrow?
Paintball your house.
Lesson?
What?
So what if we paintball your house?
Then I'll press charges on that one.
Oh!
Dude, Kramer, that's.
What are we doing tomorrow? I don't know, fine.
Supreme drop. So that's a really good drop. That's a really good drop. There's a helmet that is retailing for like 700. That's like reselling for like.
Probably a
I'll
review
just
for
be
a
going
test.
Friday night
1,500.
then.
Yeah, my guess, guys, is probably a test Monday.
Oh, what's Thursday then?
This weekend.
This week? Probably the last lesson. Thursday's tomorrow. Thursday's tomorrow, right?
Yeah.
Supreme drops.
Seriously
Seriously
though.
though.
Get the homework in. Because
Do your parents know that you do this during school?
No, but they know that I do it.
I'll have to send your dad a little Italy text.
and be like, hey,
What?
Little diddly.
like, everybody, hey, do you?
Wait, no, I can't.
Well, I can't. I would do it in school, but I can't.
Yeah.
Yeah, because you shouldn't.
Diddly diddly.
Andrew does it, and AJ does it.
Andrew barely does
Oh,
that.
Andrew and Katie are on the bridge, you can do it.
No, I'm saying they are allowed to do it.
You see how I dropped the hammer on the freshman?
Oh, wow.
Oh no.
That's
Oh.
such a good incentive.
Okay, you know what?
Wait.
I won't try to
You
go
actually
this
have the authority?
dream
I'm
job.
doing it.
To do what?
I have all the power
Dude, don't
been
pick
given to me.
Kramer, but I won't go for the supreme job tomorrow, okay?
You won't?
No, I won't.
That's really mature.
Even though I can make
He's just trying to get
500 bucks.
Okay, how about we cut a deal
How
here?
much have you made off of this?
How about
I get 40%.
yeah? How about I let you do it? If you do it, I'll take 40% of the profit.
40! Good night!
I mean, do you want 60% or 0%?
Well, it's
like
not
250
guaranteed
bucks.
I get it. So what if I don't get it?
Still gotta pay 40% whatever you have.
Then you just owe me
You
$5 commission.
Mr. Kramer's smart. He made an advantageous deal for himself. He loses nothing, but if he gains something, it's happens.
I'm gonna text my.
That's the brain.
If that's worth it or what?
Hey, no, but I got a pair of.
I'm a shrewd businessman.
Dude, it's so
You know what?
good.
Well, actually, I kind of have to be because I
Kramer.
make nothing.
Can I go grab some?
Mr. Kramer, you know why this past weekend was so good?
Why?
I got a pair of shoes that I'm gonna
Wow.
take $200 profit off.
You're going
What,
to, so
Yeezys?
you haven't yet made.
Well, they're.
Have you? Okay. Have you yet to make money doing this?
Yeah, I sold my Yeezys for 300.
And how much did you buy them for?
212.
People?
Well, with fees, I made like 50
It's
bucks.
illegal.
Okay.
What's
Nothing.
So, and then these shattered, they're both one shattered backboards.
I'm a genius.
I could
I
sell
like
them
screaming.
right
It's
now
illegal.
for like, I could make, or the app will give me like $390, and I bought them for $160.
How much have you made off?
I feel like this is more hassle than it's worth. Like you're making what, like $25 a year, $50 a day.
Those shoes are, I'm gonna make 200 off them.
You probably will end up making maybe 100, which I'm still nice.
I'm making like 200 with the fees.
So 40%, 40%.
I'll just see.
You wanna see? Are you checking that out?
Come on. I don't know, maybe. Well, it's either I get, like, I'll make that deal, but like, I don't know if it's a like, if I'm even gonna get it.
Yeah, and that's a risk I'm willing to take, I
Can we do
guess.
chemistry now?
Hey, you guys, any of you girls work size 9?
Yeah, why?
That's
Not
I'm
size
not spending
10.
$300 on
But
shoes.
yeah, men's or women's. Men's are
It's a woman's shoe that I got.
I work
size
with
9.
I'm not paying $300 for a pair of shoes.
What are they?
They're